Hi everyone, here's our research topic, Restaurant Location Intelligence in Chengdu, Spatial Patterns and Predictive Modeling of Hotspots using POI and Social Media. Here's our contents. The first part is background, and I will talk about why we choose Xiaohongshu to do our research. Xiaohongshu helps us quickly find where people like to eat and what is popular, thanks to location tags and clear topic filters. It gives real, every-time insights that are more detailed and flexible than official data, great for spotting new trends. Following that, Chengdu stands out as the perfect city for this kind of food analysis, because it is famous for food. People eat a lot, love posting reviews, and the city has diverse food spots, tourists, and rapid growth, making it a great testbed for location-based restaurant insights. To back this up, classic location theories show that where restaurants open depends on things like distance, demand, how attractive the place is, and the benefits of clustering together. Building on that, past studies show that GIS tools like density and clustering analysis are super useful for spotting restaurant hotspots and tracking location trends. Building on prior studies, our research brings in real-time social media data and machine learning to improve hotspot detection and restaurant site prediction. Continuing from this, recent research applies various machine learning techniques to analyze restaurant locations, customer preferences, and spatial trends using images, reviews, and urban data. Now, let's talk about the innovation behind our research. Previous studies had several key limitations. First, most of them lacked multi-scale spatial insights. They did not link big-picture city structure with small-scale human activity. Second, many machine learning models were black boxes, meaning it was hard to explain or apply their predictions. Also, most studies focused on Western cities, with limited relevance to fast-growing places like Chinese cities. They often gave static results, just lists or scores, and rarely used dynamic mapping or visual tools. To address this, our project fuses POI data and social media to reflect both actual and perceived demand. It connects macro urban form with micro-level hotspots in one framework. We use interpretable machine learning models like SHAP for hotspot prediction and output dynamic formats like GeoJSON and CSV for platforms such as Kepler.gl. Finally, we apply 4 spatial clustering methods to detect patterns more accurately. In short, our approach bridges multiple data sources and tools to offer a more transparent, actionable way to understand restaurant location dynamics. And here are our research aims and questions. First, we aim to explore how popular restaurants are distributed and clustered across Chengdu, based on social media hotspot data. Second, we want to understand how restaurant popularity relates to urban features, like transport, population, and surrounding services, by using both correlation analysis and machine learning. Lastly, we seek to identify spatial mismatches to help find new opportunity zones for future restaurant development. This leads to 3 main research questions. Where are popular restaurants located? What factors influence that popularity? And which areas show strong potential for new restaurant openings? Following our research aims, here is an overview of our workflow and methodology. We start with data collection using keyword-based search on Xiaohongshu and a customer web crawler to gather food-related posts. We also bring Chengdu's multi-source POI data, which includes population and 9 categories of urban facilities. Next is data preprocessing. We clean the text and remove noise, and then apply large language models and Baidu's OCR to extract information from both text and images. We match this with known locations using Google Map API and combine it to identify restaurant names and locations. Then we move on to spatial analysis using GIS techniques. We calculate nearest neighbor distance to evaluate clustering, apply kernel density estimation to detect restaurant hotspots, and overlay this with demographic and urban data to spot high potential commercial zones. We also use multi-distance clustering like Right-Place-K to explore scale-based spatial patterns. Finally, in the correlation and machine learning stage, we conduct multi-dimensional correlation analysis and apply models like linear regression, random forest, XGBoost, and light GBM to predict restaurant popularity based on urban features. To make this possible, we use Python-based reverse engineering to extract restaurant-related data from Xiaohongshu via web APIs. To guide our data collection, we created 41 keyword categories like hot pot, snacks, barbecue, and late-night food to capture different types of restaurant content from Xiaohongshu. Based on the keyword search, we collected 6,294 Xiaohongshu posts with rich metadata like user information, engagement, location, and content details for analysis, and 21,822 photos collected. As part of pre-processing, we use Baidu's OCR API to accurately extract text from food images, and innovative steps that goes beyond traditional methods, which often only analyze social media text. To summarize, Xiaohongshu data meets all 5 V's. It is large, diverse, real-time, reliable, and valuable, making it perfect for analyzing restaurant clusters and consumer trends. To support our analysis, we combined grid-based population data with multi-source POI datasets from Chengdu, like food, transport, shopping, and healthcare, to build features for correlation and machine learning models. For data pre-processing, we first worked with 6,294 Xiaohongshu posts and over 21,000 images. We removed duplicates to keep the data clean and applied Baidu's OCR to extract text directly from food images. That text was then added to the post descriptions to enrich the dataset with more meaning. Next, we use Baidu's NLP tools to identify keywords, locations, and restaurant names from both the text and tags, making it easier to analyze food types and where they were mentioned. Next, we rank posts using a popularity score based on likes, saves, comments, and shares. From that, we selected the top 1,000 most engaging restaurant posts for further analysis. Then came data cleaning. We removed posts with missing or unclear restaurant names or locations. After matching names with coordinates using Google Maps API, we finalized a clean list of 750 verified restaurants, each with popularity scores and precise geolocation, ready for spatial analysis. Based on the clean dataset, we first use the nearest neighbor distance analysis to see whether restaurants are clustered, random, or dispersed across space. And following that, we applied kernel density estimation to map out where food-related activity is most concentrated across Chengdu, helping us pinpoint the real urban food hotspots. Next, we use buffer analysis to see if these food hotspots actually line up with where people live, helping us check for mismatches between demand and population. And based on that, we classify the hotspots into 4 types, like mature, overheated, or potential areas, depending on how digital popularity aligns with location population density. Continuously, we use Right-Place-K to test how strongly these hotspots are clustered, and at what distance those clusters are most significant. Building on the spatial analysis, we then used correlation and machine learning to understand what urban features drive restaurant popularity and to predict future hotspots. As the NNDA shows, restaurant hotspots in Chengdu are not random. They are highly clustered and mostly around key urban centers like food districts or malls. Building on the previous clustering results, we found that Chengdu's top food activity hotspots are highly concentrated in just 5 central districts, showing a clear monocentric pattern. So we narrowed down our study to the top 35 checking zones to keep the focus sharp and relevant. Then, based on buffer results, we found that some peripheral hotspots lack corresponding population density, and mismatches exist between digital popularity and actual demand. Next, depending on the matching classification, the results indicate that the mature areas dominate urban core, the overheated areas are mostly located in edge zones, potential areas are mainly found in the second ring areas, and the cold spot areas are scattered and peripheral, lacking both consumer attention and residential presence. Here, we use Rapidly-K to explore how hotspots cluster across distances. We found strong clustering at all scales, especially between 100 to 800 meters, which suggests food spots are packed tightly, often at the block level. Even as distance increases, clustering still holds, just with less intensity. Building on the clustering analysis, we used a 179,285 restaurant POI dataset from Chengdu and ran correlation analysis with various urban features like population, malls, and services. We found strong co-location with services like malls, but weak ties to transit access, pointing to well-connected but underutilized zones that could be ideal for future restaurant expansion. Continuing from the spatial analysis, we use data from the 750 most popular restaurants on Xiaohongshu to explore what drives online attention. We found that service density, like fitness centers and hospitals, has the strongest link to the popularity. Commercial zones also boost visibility, while population plays a smaller role and transit access shows little impact. Building on the correlation analysis, we ran a linear regression and found that subway access is the strongest predictor on popularity, though overall the model has low accuracy, suggesting the need for more advanced nonlinear approaches like XGBoost. To follow up, the XGBoost model confirms that access to subway or bus stops is the biggest driver of urban popularity, followed by restaurant clustering, while population density actually matters less than expected. Lastly, SHAP results show population density has the strongest impact on hotspot popularity, followed by restaurants and attractions, so dense areas with dining and fun hotspots are key. To dig deeper, we compared hot and cold zones, finding that hot areas are boosted by attractions and fitness spots, while cold zones rely more on malls and transit. So finally, we broke it down by hot and cold zones, finding that what drives popularity really varies, and the best spots for investment are places with transit access plus strong restaurant clusters. To warp up, we tested different models. Random forest came out on top, but predicting popularity based only on these features is still tricky. That's why we recommend focusing on areas with good public transport and restaurant clusters, tailoring strategies for cold and hot zones separately, and improving the model by adding more geographic and demographic data. Finally, we mapped our top potential restaurant spots in Chengdu by combining heat maps of population and existing restaurants. We identified low heat zones that actually have high resource density. These are hidden gems with strong potential for restaurant development. And as we can see, this interactive map can be zoomed in to reveal the exact locations of both current hotspots and predicted opportunity clusters. For example, the marker with 3 means there are 3 potential spots nearby. Zooming in, and you'll see they are around the areas like the 蜀道大街、东大街 and 滨江东路. It is a great way to visualize not only where the hottest Xiaohongshu restaurants are, but also where our model suggests future openings should be considered. Building on the previous map, we pinpointed 10 specific high-potential restaurant locations in Chengdu. Each spot is backed by strong surrounding features like transit access, residential density, or proximity to schools and offices, but currently lacks media attention or popular restaurants. Compared to basic overlay analysis, this recommendation leverages a multi-factor machine learning model, which significantly improves prediction accuracy and helps uncover truly strategic zones for new restaurant development. For example, New metro area shows strong transit connection and moderate FNB density, but currently suffers from low media visibility. Despite its prime location near major transport hubs and mixed-use zones, it has not yet been fully tapped by popular food brands. This suggests hidden potential for attracting daily commuters and nearby residents, making it a strategic target for the new restaurant openings. Finally is our conclusion part. This study investigates the spatial intelligence of restaurant location in Chengdu by integrating social media-derived popularity data with POI and urban environmental features. The spatial distribution analysis revealed a monocentric clustering structure with popular restaurant hotspots concentrated in core districts such as Jinjiang, Wuhou, and Qinyang. These mature commercial zones exhibit both high check-in density and strong demographic support, reflecting sustained urban demand and the concept of brand agglomeration or culinary districts. In contrast, several peripheral areas demonstrate spatial mismatches, characterized by elevated digital attention but weak population or infrastructure support, highlighting the risk of overhyped or transient trends. Clustering was most prominent at 100 to 800 meters, reinforcing the importance of micro-scale planning in restaurant site selection. To address the second and third research objectives, the study employed a correlation analysis, linear regression, XGBoost modeling, and SHAP interpretability to address how urban features influence restaurant popularity. Findings reveal that restaurant density is more strongly correlated with service and commercial POIs than with population and transit alone. XGBoost and SHAP analysis confirm that clustering of restaurants and nearby amenities is the primary driver of popularity, with transit access acting as a key enabling factor. Zone-based modeling shows significant variation in feature influence across hot and cold zones, emphasizing the need for localized, context-aware decision-making. Furthermore, spatial visualization and predictive modeling helped identify high-potential but underutilized zones, including areas near Nishiko Metro Station, Huachi, and outer residential district with strong infrastructure but limited current media exposure. In summary, this research contributes a multi-layered understanding of Chengdu's restaurant and landscape by revealing spatial clustering patterns using social media data, quantifying key environmental predictors of popularity through machine learning, and proposing strategic zone-specific site recommendations for restaurant expansion. These findings reinforce the value of combining social media signals with geospatial modeling to support evidence-based, scalable restaurant location strategies in dynamic urban environments. And here are our references. That is all. Thanks for listening.